So Kamalika is our next keynote speaker. She's a professor in the Computer Science and Engineering Department at UC San Diego, also a research scientist at Meta AI. She received a Bachelor of Technology in Computer Science and Engineering in 2002 from the Indian Institute of Technology, Kanpur, and a PhD in Computer Science from the University of California at Berkeley in 2007. She did postdocs at UC San Diego and joined the CSE department there afterwards as an assistant professor. And she received an NSF CAREER Award in 2013 and a Hellman Faculty Fellowship in 2012. So thank you, Kamalika, and very excited for your talk.
Thank you, Zach, for the very nice introduction. I'm going to talk about some new work that we are doing on privacy-aware compression for federated learning. And this is based on, joint work with Chuan Guo, Mike Rabat, and Pierre Stock, who are all at Meta AI. So this is, with my colleagues at Meta AI. Okay, so, this is a workshop about federated learning. So, we are all kind of aware overall on, the kind of problems that we are looking at. We have users, when we have a big server which is trying to train a large model, and what happens is that the users would send local updates based on their local data, and then the server aggregates this together and kind of returns the aggregated model, right? And here the reason why we all care about this stuff is because this allows raw sensitive data to stay on device, and only aggregation happens on the server right after a certain amount of sanitization. Okay. So what are some of the challenges in federated learning? Well, there are a lot of challenges, and the entire morning people have talked about many of them. Two challenges that I am going to talk about in this particular talk is, one is rigorous privacy guarantees, and two is communication efficiency. Okay, so what do I mean by rigorous privacy guarantees? How do we measure privacy? So here what we are going to do is we are going to go ahead and measure privacy in the local model, right? So what does this mean? What this means is that you have each of the users, right? And each user runs their privacy mechanism. And then after whatever they have to send has been sanitized, they send the sanitized version to the aggregator. Okay, so just to emphasize, what is happening is that the curator is not trusted, right? So the aggregator is not trusted at all. And, you can see that red dashed line, that is the privacy barrier, right? So the aggregator is not trusted. After each user will run their own privacy mechanism, and then after they sanitize, their data or gradients or whatever updates they have, they communicate the sanitized update to the aggregator. Okay, and how do we measure privacy in this model? Well, what we will use here is something called local differential privacy. We say that the mechanism is epsilon delta local differentially private if for all users J and all subsets of the range of the mechanism, the probability that M of uj lies in a set S is at most e to the epsilon times the probability that M of uj prime lies in that set S plus delta. Okay, so if what this means is that I have a data point U, suppose my data point changes to something else, to the aggregator, this would be indistinguishable, right? Modulo, epsilon delta parameters. Okay. So there are, two major challenges. If you recall, these are the two major challenges that I mentioned a couple of minutes ago. So one is rigorous privacy guarantees. And when I say rigorous privacy guarantees, what I mean is local differential privacy. And the second is communication efficiency. And here what we will look at is number of bits that are communicated per client per iteration, right? And, as we will see in a little bit, these two challenges may interact, right? Which leads to a bit of trouble. Okay, so moving on, let us first look at why does naively combining privacy with compression algorithms not work. Okay, so to understand this, let us start with a very simple example where, forget about federated learning. All we are trying to do is talk about a single scalar, right? So each client has a single scalar value, x1, xi. That lies between 0 and 1, single bounded scalar value. And what we are looking to do is we are looking to compute the mean at the aggregator. Okay, so the clients will have the scalar value, they transform it using this privacy mechanism, they communicate it to the aggregator, which tries to compute the mean. Okay. So now, if you try to do this with local differential privacy, well, the simplest thing is to add Gaussian noise, and then the standard deviation of this Gaussian noise. So this is zero mean Gaussian noise, and the standard deviation is going to be calibrated to the range, right? And so that's what each client will send. And this is kind of what you would get, right? So here what this histogram is a whole bunch of client responses. This is what the client responses would look like, right? And let's say the true client value is the same, but because you're adding a Gaussian, the responses would follow a Gaussian distribution, right? And if you aggregate them, right, the aggregated mean would be, the mean of this Gaussian distribution, which would essentially be the true mean, right? So if you were just using local differential privacy, then you would be doing the right thing, okay? What about compression? Well, for this sort of cases, it turns out one of the simplest compression mechanisms that people use is something called dithering, right? So what does dithering do? Dithering, what it would do is that it would break up 0 to 1, this entire interval 0 to 1, into a grid of size 2 to the b, right? Capital B equal to 2 to the b, so that it can be communicated using small b bits. And then if your x falls into one of these intervals between I over b minus 1 to I plus 1 over b minus 1, then with some probability it will round to the side, and with some other probability it will round to the other side, right, to one of the ends of the interval. And the probabilities would be adjusted so that it's unbiased, right? On expectation, you will still transmit x, but you will be transmitting one of the grid points so that you can compress, okay? And here also, if you look at the true mean and the aggregated mean, well, this is the kind of distribution that you would get. The histogram gives you the distribution that you would get. And, the true mean would be, it essentially overlaps with the aggregated mean, okay? So this raises the question, what would happen if we use both at the same time, right? So we did privacy, by adding the requisite amount of Gaussian noise, and then we do the dithering to compress. And here is what we would get, okay? So what you can see over here is what happened was, so what happened was the following. What happened was that you had this Gaussian, and then the Gaussian kind of got clipped away, right? And because the interval was 0 to 1, the true mean is a little bit more than 0.5. It's not exactly at 0.5. It wasn't symmetric, right? So it got clipped away, right? So it got clipped away. One side got clipped more than the other, and as a result, even if we got a lot of, even if we had a lot of clients which were giving us, compressed, private and compressed versions of the same answer, what we got was a large difference between the true mean and the aggregated mean. Okay, so and this serves to show us that if we just kind of naively apply privacy mechanisms followed by, like standard privacy mechanisms followed by standard compression mechanisms, then we may not get the results that we desire. Okay. So what do we need for privacy and compression? So let us first take a closer look at what went wrong over here and what do we need in this case. So, obviously privacy, that is not of any debate. And then compression, right? So these are the two, constraints of the problem. But it turns out that if we want the aggregator to be doing the right thing, we are also going to need at least this one other condition that we call asymptotic consistency. What does asymptotic consistency mean? What it means is that if you have an aggregator which is taking the responses of the clients and let's just say they're aggregating it together by summing. I mean, you can also think about other kinds of aggregation and, the conditions would change and so on, but that's a different matter. But let's say if you have an aggregator who is taking in the responses of the clients and aggregating them through summing, then as n goes to infinity, in the sense that as you get more and more and more clients, that aggregate should converge to the right answer, right? If we didn't have privacy, then that aggregate would have been, sum over ixi divided by n. But what this means is that as you get more and more clients, it's okay if you make mistakes when you don't have that many clients, because as you get more and more clients, you should be doing the right thing, okay? So, it's a relatively simple observation, not too hard to show, that if your mechanism is unbiased, then that is sufficient for 3, that is sufficient to ensure asymptotic consistency. And now the question is, how do we ensure conditions 1 to 3? Okay, and this is what we would look at over the rest of the talk. Okay, so we are going to design a new privacy mechanism that will achieve conditions 1 to 3. And here is how our mechanism works. First, we take our scalar x and we dither it to the input grid, right? So we have an input, we have a scalar x, we dither it to the input grid. Then we are going to map the input grid points to an output grid. And this mapping would be random, in the sense that, we need that to preserve differential privacy. And then we will encode this, so we will get, the output grid has 2 to the b points, and then we will encode the output using small b bits, okay? One thing to remember is that dithering is already unbiased. So, that's good, because we need the client mechanism, the privacy mechanism, to be unbiased. So dithering already, gets you there, in the sense that dithering already gets you something unbiased. So that is good. And now, what do we need of the privacy mechanism? Well, the privacy mechanism, or the map over here, right? So dithering, that step is already unbiased. The map over here, right, step number 2, should satisfy both privacy and unbiasedness, okay? So how can we do this? Well, so remember I said that this is a randomized map, and if pjk is the probability of mapping input j to output k, and ai is the output alphabet I, then it turns out we can write out these constraints, okay? And so the constraints, if you want to ensure epsilon local differential privacy, here is, this is the, it's a linear constraint. So you can write out a constraint involving pjks, okay? Unbiasedness can also be written in terms of a constraint. This is a bilinear constraint. It involves both ai and pji, right? This is our unbiasedness constraint. And finally, we need a constraint that shows that, that ensures that the pjks are probabilities. So, this is basically it just saying that it lies in the probability simplex. So that is the probability constraint, okay? And so if we can find these pjks and ais that satisfy all these constraints, what we would have is a feasible, a feasible solution, right? That achieves privacy and compression. And what do we need? Well, of course, we need accuracy. And to achieve accuracy, what we could do is we could, enforce these constraints, and subject to these constraints, we can minimize the output variance, right? And that's what we will be doing. Okay, so this is our output variance. And if you can solve this, so this is an optimization problem. It's not a linear program. It's actually a non-convex optimization problem. And if you can solve this optimization problem, then the solution to this is what we call the minimum variance unbiased, or MVU mechanism. Okay, so this is our mechanism. Okay, so to give you a picture of the full algorithm, this is what we do. We are given this B in, B out privacy parameters. We solve this MVU optimization. This is this optimization problem that I just showed you to get the alphabet and probabilities. Okay, and now we know what the mechanism looks like. And then when you're given an input X, you do your dithering to the grid of size B in. You can map input grid point, and then you do your mapping using this randomized map, and then encode the output in B bits and send it over. Okay, so this is our full mechanism. Okay, how does it work? So here is an example of our mechanism where we are estimating a mean of scalars x1 to xn in -1 to 1. Okay. And here are some results that you will see with, with various mechanisms. So on the x-axis, you have these x's, right? So each x is, the x is the actual mean. And here we are assuming that every data point, every client has the same x, just to keep things simple. Of course, it will work even if it doesn't. So, right. So every data point has the same mean. And on the y-axis, what we are doing is we are plotting the variance, right? So what we see over here is what happens when, so what do you get out of the MVU mechanism, right? What is the variance that you get out of the MVU mechanism as x varies from -1 to 1, right? And as you can see for, and we are looking at MVU with, 1 bit as well as 3 bits. So as expected with 3 bits, as you increase the number of bits, your variance goes down. And, for b equal to 3, at least for large epsilon, this seems almost as accurate as Laplace. By the way, the dotted line is Laplace, right? Which is the Laplace mechanism, which is like a standard mechanism for epsilon differential privacy. And the Laplace mechanism is not using any compression. So, this is, so this is the full, this is the full Laplace mechanism without using any compression. Okay, so this is what we get from distributed mean estimation. Okay, so that was, that was great. We managed to do it for scalars. And now the question is what happens when you have vectors, right? So one plausible solution that you could do is you could solve a high dimensional MVU problem, but this will have a lot of variables and a lot of constraints. So the running time will be exponential indeed. Okay. 2 is we could compose across coordinates, right? We could solve the MVU for each coordinate and compose across coordinates. And if you do that naively, then you would get a factor of D, right? And so your privacy guarantee would not be as great, okay? So before I get to what we actually do, let me take a very brief detour to talk about a slight variation of differential privacy called metric differential privacy, right? Or, this is in the local model, so metric local differential privacy, okay? So we say mechanism is epsilon metric local differential privacy with respect to a metric D if for all S and T in the domain of M and all subsets of its range, the probability that M of S lies in a set S is e to the epsilon times D of ST times the probability that M of T lies in the set S. Okay, so the difference between this and actual differential privacy is that this epsilon parameter would be constant for actual DP, right? Whereas for metric DP, if your S and T are close, then the distribution should be even closer, right? And so the difference in the distributions, M of S and M of T, depends on how close S and T themselves are, right? So this is metric local DP. So why do we care about metric local DP? The reason why we care about metric local DP is a theorem that we can show in context of our algorithm. So the theorem that we can show is that if each coordinate, if the mechanism that you use to encode each coordinate is epsilon metric DP, then when you output the union of that, the entire thing is epsilon DP, assuming that the entire length of the vector is 1. Right? So what this means is if we can ensure metric DP per coordinate, then when we look at the entire vector, we can get epsilon DP, and we don't need to add a factor of D. Okay, so what we need to do if we want to use this kind of composition is to use per coordinate metric DP. Okay, so how do we do that? Well, in MBU, we just got differential privacy by enforcing a constraint. So we can enforce a constraint like that, right? And that would work. But it would give us metric DP only for those x's that lie on the input grid, right? And in fact, what we can show is that dithering will destroy the metric DP guarantee, right? Because 2 points which are very close may not get dithered to the same points, and that will destroy the metric DP guarantee, okay? So what we need instead of dithering is a better rounding solution. And that leads us to our new idea, which is the interpolated MBU mechanisms. Recall that in dithering, what happened was that we were kind of linearly interpolating between the grid points. In interpolated MBU, we do things a little differently. And here is what we do. We look at the distribution, the Pij distribution of so if your X lies between, let's say, grid point I and I plus 1, we look at Pij and Pi plus 1j and interpolate that in the log likelihood space. So some of you guys who are familiar with a lot of differential privacy might recognize kind of whiffs of the exponential mechanism. And in some sense, that is kind of what is going on here. Right? So this is what we do. And I won't go into a lot of details, but essentially this is what the algorithm becomes. First, you solve your MBU mechanism to get the probabilities on the grid. And then on the input that lies between grid points xi and xi plus 1, you sample from, you sample from this interpolated distribution. Okay. And what we can what we can show is that if your Pij satisfy epsilon metric dp on the input grid, then this mechanism will satisfy 2 epsilon metric dp, right? And the factor of 2 is, for those of you who are familiar with the exponential mechanism, the factor of 2 is for exactly the same reason as the exponential mechanism analysis. And then it turns out if we only have b in equal to 2, right? So if we have 2 points in our input grid, we can get an even finer analysis and do quite a bit better. Okay. Okay, so now I will finally come to how this thing works. Here we are looking at DPSGD with the Gaussian mechanism replaced by MBU or interpolated MBU, and B in is equal to 2. So we are using the more sophisticated analysis. And again, here the output number of bits is 1 per coordinate. Okay, so we are transmitting the entire a vector. If our gradient is d-dimensional, we are transmitting d bits. Okay, our baseline here is, of course, the Gaussian mechanism, which is at full precision. So you can think of b equal to infinity. Then there is sine SGD, which is another baseline here, where you just add Gaussian noise and output the sine of that. Right, that is the baseline. And then we have our 2 mechanisms, MVU and IMVU. And what we see is that IMVU performs almost as well as the Gaussian mechanism. Right, MVU sometimes falls short, sine SGD sometimes falls short, but IMVU performs almost as well. Okay. So this is another experiment on federated learning with sample level DP on FMNIST. And here each client has a predefined split of about 230 samples. Again, what we find is that IMVU with 1 bit performs almost as well as the Gaussian mechanism. Okay. So in conclusion, what we have found so far is that IMVU seems to be a really good replacement for the Gaussian mechanism if you want to do locally private federated learning with communication constraints. And a lot of kind of technical contributions and math went into it. And kind of the 2 main ideas over here is constructing a mechanism by solving an optimization problem. People had done this kind of thing before, especially in the context of like geo-indistinguishability. But what we have is a new optimization problem. To our knowledge, this particular problem I haven't seen before. And then the second kind of another technical contribution was a finer privacy analysis. And with this, let me end my talk by thanking my 3 collaborators, Chuan, Go, Pierre Stock, and Mike Rabat. And this work was done at Meta AI. Thank you.
Thank you so much, Kamalika. That was excellent. We have 1 question in the Q&A, which we can get to, but first I want to solicit audience questions. Please, if you have a question, you can chime in or post something in the Q&A or add something in the comment. Yeah. Maybe just to start, Vitaly, I see you just fielded a question. Maybe you want to ask it in person?
Yeah, sure. I just want to mention that that the problem of estimating high dimensional mean with local differential privacy has been studied for quite a bit, and by a few people here. And at this point, we basically know both what the optimal algorithm, if you require unbiasedness, is, like what's the best achievable error, and also how to achieve it with low communication. So I was sort of wondering how, how
Right. So we
does this
did
compare to the stuff
compare
we've been
with,
doing?
so the first part is the MBU, right, which applies to distributed mean estimation, where we have this unbiasedness constraint. There we did compare with, it is true, there is a lot of stuff. We did compare with CLDP, which I think was a Google thing, which did, and we did better. If you can point me to your work, we are also happy to compare with it in the, in the final version. I don't know which specific one you are talking about, but we are also happy to compare with it.
The algorithm is originating in earlier work by folks at Apple. Preview it, we showed that if you optimize it, we gave an algorithm. We first gave a way to compress it, and then we actually more recently we showed that it's actually optimal. The best achievable, even if you don't place a constraint, a communication constraint.
I see, but is it for, yeah, so please send me the paper. We'll be happy to compare against
Sure,
it.
sure. I actually just post those papers right here in the
okay.
chat.
So one other thing is that with the pure DP guarantees, the algorithms that have pure DP guarantees, we looked at a couple, but because, we don't have pure DP, right? We have epsilon delta, and we are using, Renyi composition. So I think some of the pure DP style algorithms, as a result of that, they don't fall short. As a result of that.
I disagree with you. Just basically in the local model, there is essentially no difference between pure DP and epsilon delta, because that's also a simple transformation. That's just because this epsilon can't affect much when you're working with a single input, but that's maybe a separate discussion.
For the federated learning thing, right. So for the federated learning thing, you do need the multiple composition, because you are not just for distributed mean estimation, you are sending it once and then you are done. For federated learning, you need, right, like the same person is sending out multiple gradients, so you do need Renyi composition.
I agree, but you can compose from pure DP, and then you will
get
absolutely.
At the end, won't be as good as Renyi.
You
know this very well with Renyi.
Yes, of course.
Sewon, please go ahead.
Hi, thanks for the nice talk, Kamalika. I noticed that for the federated learning, you did sample level DP. Was it a particular reason that you didn't do user level DP?
Not really. Not really. No.
I see. It would work either way. It's just the choice.
Yeah. I mean, these are like just a subset of our experiments, right? So.
Sure. Thank you.
Peter, go ahead.
Hey, Kamalika. So I'm wondering, why did you use uniform subdivision of the interval for the dithering and not exponential subdivision?
That is a good question. So for uniform subdivision, the reason why did we use uniform subdivision? Mostly because, we just got the maths to work. Yeah, that's a good question. I mean, yeah, it might also work for exponential subdivision. The thing is that we ended up not using dithering at the very end, right? We ended up using interpolation at the very end.
And the reason why I'm asking is because dithering with exponential subdivision has also exponentially lower variance than the uniform subdivision.
Right, I know, but here what happens is that, the variance due to the privacy really overwhelms the variance due to compression. That is, so in this case, you could maybe change some things, but the compression scheme, but it doesn't help too much because,
so even the
exponential variance due to privacy.
Okay, it's interesting. Thank you.
I think we have time for one last question if somebody in the audience. We have one over Q&A if nobody else has a live question. Peter, go ahead.
Yeah, maybe this is a comment to a follow-up comment to what Vitali said. Maybe Kamalika's approach is efficient in terms of encoding even at large epsilons, because it does not use these rejection sampling type methods. So that could be perhaps an added value here, although I'm not very familiar with Kamalika's approach, so I'm not sure what the computational cost is at large values of epsilon, of local epsilons. But that could be potentially something to take into account.
Yeah, good. Yeah, sorry, right. There's some of the techniques have exponential dependence in the rejection sampling, although we know that if you are willing to give up a little bit in error relative to the very optimum, you can remove that dependence as well.
Is this the Gaussian per unit approach?
No, it's not Gaussian per unit. It's just by splitting, instead of sending just one encoding, you can
I see.
You can do repeated. You basically repeat the mechanism with smaller epsilon. And if epsilon is, once the epsilon is like 8, you're very close to asymptotic optimality already. So it's just it's a way to replace the exponential dependence with linear dependence at a relatively small expense. There is still a good question of what you should be doing in practice. And I agree that it's not obvious, like given certain constraints, how things will turn out. But certainly that's why I think would be interesting to see those methods compared.
Okay, yeah, no, thank you. Just to double check, I was looking for what happened in ICML 21. You were talking about this lossless compression of efficient private local randomizers, right?
Yes. This is the way where we show that how to do it optimally. So this year we proved that what was there is actually the best achievable, and it's to work with Hilal SC. There we just present the protocol but the proof of optimality, which by the way also goes through.
I think Vitali, you and I both know that there is optimal and then there is optimal. But anyway,
it's optimal. It's truly optimal, and it does go via optimization. In the sense that we discretize the space sufficiently well and show that what we do is optimal. I mean optimal, including like first order terms, like no constant, just undeception of unbiased. That's the only thing we assume.
Absolutely.
Yeah.
I'm going to jump in here. Thank you all for the discussion. I encourage you to connect offline or through the chat feature.